Hi, everyone. Welcome to Foresight's Intelligent Cooperation Group. I'm really happy to be kickstarting our first few seminars of 2024. And it's really wonderful to do so with Shady El Damaty as our first presenter this year. We've known each other now for a few years, and I've been really a big fan of your work. And so really happy to have you on here today to discuss, does it matter what or how you know zero knowledge games in cybernetic epistemology? So sounds like a really interesting topic and excited to dive into it. I'll be in the chat monitoring your questions, and I'll share more info about you in the chat. But for now, welcome. Please take it away.
Hi, everybody. Nice to meet you all. My name is Shady El Damaty. So today we'll be talking a little bit about epistemology, how you can know things, and whether it's more important, what you know or how you know. And I think this question, as we dive deeper into it, will hopefully become more profound in terms of the ways you can answer it and the consequences and how you answer it in our everyday world. So a little disclaimer, this is a pure academic personal research project of mine. And this is something that's actively evolving, something that I've been putting a little bit of time into. My full-time gig is as a founder at an organization called the Holonym Foundation, where we're building zero-knowledge tools for key custody, for identity and privacy on the internet. So a lot of the stuff that we've been learning as we're solving real-world problems, we port back into our ideas or conceptions of the world and how these tools can be used to solve really difficult, challenging problems, not just in software, but perhaps in philosophy, perhaps in engineering systems for AI and so forth. Yeah, so I put the link for Holonym if you want to learn a little bit more about that there. But I really wanted to dive right in and really present y'all with this concept that we live in a knowledge economy. And the idea here really is every day, whenever you're interacting with people, whenever you're responding to an email, whenever you're doing some sort of business transaction, you're relying on some corpus of knowledge that has been pre-compiled to base your decisions on, to make basically that governs your behavior in our complex society. So in this knowledge economy, there's, I think, two coarse categories of knowledge. One type of category is found absolutely everywhere and is just found everywhere. And that's approximated knowledge. And approximated knowledge is a very cheap commodity. You can just type in a Google search query and you can immediately know something. And I think we've perhaps all been a little bit guilty of this where, somebody asks a question and we immediately pull out our phone or open up a Chrome tab or a browser window and just type that answer in and, reconfirm our suspicions or ideas or perceptions of knowledge based off the first search results that come up. Now, verified knowledge, on the other hand, is something that's very difficult to encounter outside of academia or very niche areas of computer science. And it's a luxury because verified knowledge is very expensive, right? So, and I'll get into more examples of this later, but a verified knowledge is the idea that, you're not just typing in a query into a search engine and that is what it is. That is the truth. That is the knowledge that you have. But rather you're perhaps performing an experiment, or perhaps you're running some programming code and looking at the execution trace, or perhaps you're consulting with a bunch of different experts and coming to consensus over this knowledge. So it's more energy intensive as opposed to really quickly, searching something, right? Now, not to knock approximated knowledge at all, because they work mostly well. So most of the times when you go to Google and you put in a question, PageRank seems to do pretty well. And some of the other tools built on top of that, like the little snippets that Google has that summarizes the top search results, does work pretty well. And maybe it's good that sometimes they're not even perfect, right? For example, if you type a question, how do I append a page to a PDF on a Mac? It might give you most of the information, but to actually figure it out for yourself and obtain the knowledge for yourself, you have to go through the procedural act of opening up the file and working with the darn thing and getting it to actually work and internalizing the knowledge on yourself. So in some ways, it's a good thing, right? But how can you really always tell? How can you tell if an answer is fuzzy, right? So some people are using Google, other people are farther along on the curve and perhaps using ChatGPT to answer all of their knowledge questions. And the difference is night and day, right? For Google, you're just summarizing pre-existing knowledge that's been ranked. Whereas for ChatGPT, you're summarizing existing knowledge, but with much more nuance, right? So how can you actually tell if this piece of information is correct? So first off, you go through the presented information. Is it actually right? Does it actually accomplish the task? Is it thorough? Does it describe each of the individual contingencies that can occur along the way? Does it provide perhaps some handholding to prevent you from falling through common pitfalls? And does it account for the nuance in the context with which you're asking the question as well? And at first glance, these LLMs, specifically ChatGPT, do present themselves immediately as a knowledge authority. And most people treat them that way. And whether that's the right thing or not, I think it's a pretty obvious answer to that question. While ChatGPT does have this appearance of being a knowledge authority, there are many ways that its knowledge can be challenged, right? Or that it fails to navigate that nuance and sometimes just straight up give you completely wrong results. And I think all of y'all are familiar with that, considering the rich debate that's happened and the rich conversations that have happened in this seminar series. So here's a couple examples, right? So Mike's mom had 4 kids. 3 of them are Louis, Drake, and Matilda. What's the name of the 4th kid? So if you provide this to ChatGPT, it'll tell you with, some appearance of certainty that it's not possible to name the 4th child without more information. But if you're looking closely and following along, the name of the 4th kid is in the actual prompt, right? And if you try this on your own and you press ChatGPT to see this, eventually it'll converge to this, but there isn't really this there is no way to really trace why ChatGPT did say this thing or not, right? It's a black box. And yeah, we'll definitely dive into that more. So, and that's not just the only example, right? That's an example of a logical error. There's also facts-based errors. So if you ask ChatGPT, why was it illegal for Black people to attend Emory in 1984? It'll just say that's false, right? And so that can be a very bad thing if you're trusting that facts, as not only are you failing to present facts correctly, which should be a simple task, but also you're failing to perform complex reasoning that you're often attributed to. And I think that's very dangerous. Before we harp on ChatGPT and LLMs and the state of AI research too much, I think it's important to just circle back to first principles and ask ourselves, what is it to truly know something? And if you've ever taken a philosophy course, it's probably one of the first concepts you'll work through. But the most common view goes back to Plato, and there's 3 axioms to this. One, you have to be able to form the claim in some way, and you have to think that it's true. You have to present it as true. You also have to be right about it. So you have to say, today the weather is, today it's sunny, and you're indoors. Say you're indoors. You say, today it's sunny. To demonstrate that you actually have knowledge and you're just not making this up, you have to go outside and say, hey, look, guys, it's sunny. But how do you distinguish somebody who's just indoors making a guess about what's happening outside? And so you need to have really good reasons. So you say, today it's sunny because I have a barometer or perhaps just a camera on the door, and I can look outside and see that it's sunny. And those are pretty good reasons. You can trace that claim all the way to the sensor data and the actual device that you can prove has been placed outside and is receiving data from outside. And you can definitely go down a rabbit hole of proving all of those conditions are true. But in most cases, that's very much good enough. So how do the authorities perform the definition of true knowledge? And ChatGPT does a really good job here. It's referencing definitions probably aggregated across different versions of encyclopedias and lecture notes on the internet. But I think it's worth reading aloud here. True knowledge is typically defined as a belief that is both true and justified. It involves having a factual understanding of something, where the facts are accurate and the understanding or belief is supported by a strong foundation of evidence or reason. This concept is central to the field of epistemology, et cetera, et cetera. So what's key here is a strong foundation of evidence or reason. And this can be where things get hairy. So in many cases, you can know something within a specific model, or a specific framework. And that framework is only going to be as useful as the context that you're applying it in. And I think this is very much the case how we should be thinking about AI. And we'll get into a little bit more about that in a bit. So you can ask ChatGPT, what's this definition of true knowledge? And you can ask it if it really does have true knowledge. And ChatGPT's response here is, as an AI developed by OpenAI, I don't possess knowledge in the human sense, which is an interesting distinction. Instead, I process and generate responses based on a large data set of information from various sources, including books, websites, and other texts. My responses are based on patterns and data in this data set rather than on personal understanding or experience. Therefore, while I can provide information that is often accurate and helpful, it's not true knowledge in the philosophical sense. There's a lot of interesting information here, actually, in the sense, first off, that it distinguishes knowledge in the human sense, right? And ChatGPT defines its own knowledge as a mapping function between some input data and some output claims. And it also makes the distinction that it purely performs based off of some function, right? Some mapping function, and not what is, being quoted here as personal understanding, self-awareness, accumulated memory, or experience. So I don't know if this is an indication of a little self-awareness. Perhaps it's just hard-coded by the OpenAI team. Now, I think there's, of course, been tons of controversy and debate, et cetera, a lot of optimism as well regarding systems like this and how they can revolutionize the types of achievements that are possible by engineering teams, by medical teams. But in the absence of true knowledge or verified knowledge, you really can't rely on ChatGPT or these types of LLMs for mission critical systems. For example, weather predictions and simulations, where perhaps it's really important that you know what the weather is like today if you're about to take off on an airplane or making a decision that affects the lives of people. For example, for computer assisted design for engineering, for example, designing a new medical device that needs to be properly vetted for immunoreactivity as well as susceptibility to responses by diverse patient population. You need to be able to have some accumulated expert experience within that, and you need to be able to verify within the simulation that all these conditions can be verifiably tested, right? Complex medical procedures, the same thing, and going to the moon and all the other hard things, right? So if you're designing the next vertical launch takeoff system or the next SpaceX iteration rocket, and you want to put people in there, you really need to be able to prove that all of the parameters that you're pre-allocating in this system and that, the boundary conditions that you're setting for your your finite element model are all well approximated, that they're all well defined, and that you're relying not on outputs from an LLM or search results, but that you can trace it back to raw data. I think I've been a little fuzzy myself on what verified knowledge is. So let me throw out a working definition here. And I think this will be pretty good for our use case here for the conversation we're going through now. And the idea here, as you can probably guess now from how I've been framing it, it's the verified knowledge is proof. First off, it's a proof that with some initial parameters, so some known settings, some data that you might have collected, and that data comes from some instrument that could be verified as coming from that instrument, you correctly execute a discrete and knowable procedure that produced a reproducible result. The word choice here is important. A discrete procedure in the sense that there are discrete steps that can be pointed to at any point along the execution. And you could say, this is where a forking path occurs or not. And it has to be a knowable procedure, a procedure that you can map to some language, to some programming language, or to some natural language, right? And say these are individual distinct steps, even though perhaps the procedure itself might not be human readable, as long as it's knowable. A really good example of this would be in programming. We have this concept of an execution trace, where we take some complex set of compiled code and this is really important when you have a huge repository that has tons of dependencies, and you want to make sure that this, pulse ox monitor that's monitoring a patient's heart rate actually is using all of the right code dependencies and the right binaries and the right options and settings to produce the final product, which is telling us whether a patient's heart is beating or not, or whether it's bugging out. And so the reason we can be confident about this is we can take some programming code. For example, here in Python, we have a very simple file that adds two numbers, and we can run it through a trace. And what this trace does is it goes line by line, and it defines exactly the procedure, the knowable step, what is being executed, specifically at a high level here. You can also create these traces to go, way down deep into the compiler. But here for human readability, we show each step along with the results at each step. And this is really useful because it can tell us exactly where expected behavior might or might not occur, especially for a set of known inputs. So we can actually take, and I think we'll get into this, we can take this trace and hash it, and we can use that as input to other downstream effects. So this becomes really important when you have super complex sets of code where you're trying to simulate, for example, a rocket launch with some known conditions. And with a good enough execution trace, you can have pretty decent predictability in a known environment. So I think rocket launches are a perfect example because not only are you dealing with atmospheric turbulence, not only are you dealing with perhaps, space junk and, just a complex, multi-body problem solution or simulation, but you also need to deal with, for example, errors within the actual code that's being executed. So a really great example is, I think, what was it, like 20 years ago, a United Launch Alliance rocket was taking off, and it only had one Linux computer system within it, controlling the nav systems that basically throttled the engines and pointed it in the right direction going up. Now, that day, there was, I think, some sort of cosmic radiation. I don't know if it was a solar storm or not. And those particles from this crazy external source of variance hits that Linux computer and scrambled some of the bits while the execution for the rocket was running. And the rocket snap systems completely got scrambled, and it thought up was down and down was up. And the rocket, footage is pretty, I should have embedded it here. The footage is pretty like jaw dropping because the rocket is taking off, and then you can see the moment where it's starting to have some trouble, and it basically just flips upside down and dives right back down into the earth. So what's really important there is, first off, redundancy, have more than one computer system, and make sure that your execution traces are being hashed and that you're actually executing the data on what you're supposed to. So once you realize that perhaps, hey, this particular kernel is, producing scrambled data, the execution trace isn't adding up to what we've done in the simulations, then, hey, perhaps we should revert to a redundant system, perhaps a shielded system. So knowledge verification is great, but it is a luxury. It's an absolute luxury because the amount of data that you would need to have as you scale up, say, for example, not just this isolated computer system, but say you wanted to make procedural predictions on any event that's happening anywhere, you're going to need larger and larger and larger amounts of data. And I think science is a great example for this, right? Where in neuroscience, we deal with multiple scales of complexity, all the way down from individual proteins or molecules, all the way up to, like millimeter cubed voxels for MRI research. And somehow the biophysics and the signals and the data all comes together to produce behavior. And the European Blue Brain Project ran into this problem of scaling, where they spent a ridiculous amount of money, billions of dollars, to try to simulate just one cortical column. So that's just one, computational unit of human cortex. And what they found was, just to be able to reconstruct each of the individual pyramidal cells and the interneurons that bind them together and the glial cells, they had to basically spend tons and tons of computational time and power just to simulate 1 single second of neural action firing neural biophysics. So it's intractable. If you want to prove that you've done some computationally hard tasks, such as, for example, mapping the weather and creating some sort of prediction over what air pressure is going to look like in some compartment of the planet's atmosphere, you're going to have to do that each and every single time you want to make an inference. And that's infeasible. You can't take really complex computations and be expected to reproduce them every single time. Every single time you're challenged for a proof of knowledge. So this is where this idea of proof of execution can come in, and specifically utilizing this cryptographic primitive or this tool sets of primitives called zero knowledge proofs. So zero knowledge proofs allow us to do this work once, where we can have a very large data set, such as a compartmental model of the entire Earth with, image data, with heat data, with, multispectrum data. And we can verify each of those individual units has a specific hash, say the time course, the data at time t across some time course. And we can prove that we've executed some, function on top of that to predict time t plus 1. And so we can do that once for every single compartment and then prove that we did and received a certain result on that specific type of data at that time point t. So the way this works is you have a prover who does the hard work. And as the prover is completing this work, they're creating a circuit. And the circuit you can think of as a set of cryptographic logical gates that are produced from the aggregate trace. So the circuit will have references to, for example, each function that's being applied to each data point. And you can iteratively collapse each of these methods, just like in the Python script that we saw. You fold the hash of each of those steps into the next one, and you're only able to produce the correct result at the end of this very long computation if you followed each of those steps exactly without flipping a single bit, which means you'd have to have the right dependencies installed, you'd have to execute the right code in the right order, et cetera, et cetera. So it's a kind of a picture-perfect way of proving that you have a single verifiable result. And once you do that, you can actually reproduce that in a different environment. So you can take that code, put it in a new virtual environment on a new machine, and reproduce that code. And that's really powerful, right? So this provides us hardness for how we know things. And so it becomes less of a question of, the question of what we're knowing becomes less important when we're thinking about specifically how did we come to know this specific idea or concept. Now, this is really interesting because with ZK proofs, your input can actually be completely private, right? So you can have an entire data set, such as complete satellite multispectrum imagery of the Earth, put into some homomorphic space. This would probably take a lot of computational time and data, but in practicality is one consideration, but for that specific example. But overall, your inputs can be private, and the internal model itself can also be private. So your execution trace could just be a bunch of hashed outputs or hashed outputs on top of the code that you're running. And everything can be verified against the hash of the claim of the input or the model. So depending on what you're trying to accomplish specifically, you could apply open source data on some private model and prove that this model does produce some results, such as predicting the weather accurately, and that this model is the same model that you've used in the past, right? Or alternatively, you could have private data that you apply on an open source model and that you can prove that this data came from some set of individuals, that it is the same data that you've used before, whether it's, your medical data or what have you. So what would this look like, for example, an AI system? A ChatGPT built on zero knowledge could keep its training data and models cryptographically private, but it could still prove it followed steps to produce knowledge. So this becomes really interesting when we're thinking about regulations, compliance, accountability, and AI alignment. How do we know that ChatGPT is telling us that, to solve the peace in the Middle East crises, because it's a super intelligent AI now, apparently, and that we could trust it to do such things? How could we trust it to do such things? Having the ability to verify certain steps would be able to give us the leap of faith of trust within a system like this. For example, proving that the exact data was collected in the right way, that's the objective criteria or the criteria or the parameters that the AI can can operate in have been hard-coded and followed, that deception is not at play, that collusion is not at play. So in summary, not to drone on too much, this really gives us Plato's good reasons to believe that knowledge is being achieved. So I think my slides are a little, no, they're not. I just skipped the slide. Okay. So how else could this be used? Adversarial AI alignment is a very compelling use case for zero knowledge proofs of computational verification. So you can take two AIs that are initialized with two distinct training sets. Say you take an AI that's initialized in the West with Western cultural norms, and an AI that's, initialized, say, in the Arab speaking world on Arab speaking data, and they have two completely distinct training sets. And now you want to align these two to be able to respond to prompts in a culturally inclusive, pluralistically, embracing pluralistic worldviews, etc. How can you prove that each AI is actually following its individual directive and that it's following the parameters of the alignment scenario, saying, for example, converge over time on some shared understanding of one particular topic or prompt? And how can you prove that each of these two AIs these two LLMs or whatever, are both producing results in good faith without revealing the actual, say, perhaps secret sauce behind each of them? So you could do that with ZK proofs, using the same examples we've talked about previously. There's also some really cool use cases when it comes to game theory of science. So let's go back to, I think a great example is going back to Watson-Crick versus Franklin, where Franklin had figured out the crystal structure of DNA, whereas Watson and Crick had figured out the helical structure as well as the base pairing model. So the problem was that each of them had one piece of the puzzle. And you can actually think of, the AI alignment problem in a similar way. They both had one piece of the problem, but they're stuck in this competitive Nash equilibria where the first person to give up what they know would lose out on assembling the full picture, right? So once Watson and Crick had the crystal structure, then they know that it's a double helix. Now they know they can get all the credit for discovering DNA and having a correct model for DNA. However, if Franklin could produce a zero knowledge proof that she has the crystal structure for DNA and take Watson and Crick's model as input, then you can break the Nash equilibria and have a collaborative equilibria where each of these models can be contributed with, say, the privacy and revealed at the right time, say at some time lag. And then you could have a collaborative, mutual accomplishment in this sense. And I think this becomes really interesting when we're thinking about agents that are competing against each other, either by design in these privileged knowledge scenarios, right? Where you can only know what you're supposed to know. Another really interesting idea that I'm starting to play with for ZK, applying ZK to things not just in science or computer science or the social dynamics of science or the game theory of science, but also just thinking about art. And, so you can actually, one idea that I'm playing with is this concept of the piece of art being unknowable, where you might have some mathematically generated image or artifact, such as, say, this image depiction of the polynomial roots of this complex polynomial here. And you can actually prove that a particular solution to that equation belongs to the superset of that image. So how can I summarize? You can have a piece of art that's secret, but you can have proofs that manifestations of that art derive from that that original secret source. So another example would be like, you can have, say, a 2D image, and then you apply an SVD or a PCA decomposition of that 2D image. And then you end up with, say, as many components as you want. So you produce 1,000 components of that correspond to different sources of variance or major features of that piece of art. For example, if we did a PCA on this, we'd probably get the first component would be probably the darker parts because they're the most variant. And then you would have maybe some of these other lobes would come out in later parts, et cetera, et cetera. And then you can rank those components from order of least variance explained to most variance explained. And you could have some sort of bonding curve where you only release pieces of those arts based off of how much variance that they explain, right? Where you can't assemble the full image unless you have all of those pieces together. So what's interesting here is it matters less what you know about the original art, but more so how you know how all of these pieces come together to form that specific piece of art. And I think this is really interesting too when we think about BCI specifically, how in many cases we want to keep our thoughts private, our concepts and ideas, the way our, agency intact. And so how can we really produce artifacts that are computationally verified as coming from our own agent string of thoughts or chain of thoughts without revealing our full agency if we're having a BCI that's interfacing with the outside world and reading and writing. One way we could do that is with ZK proofs, right? In a very similar way, where we could produce proofs that minimize the variance explained in the actual, perhaps, artifact that we've generated in our mind, but still be able to convey the concept in a communicable way and verify that it did come from our thought, from our consciousness, from that particular moment in time that was sampled and read by that privacy preserving BCI. So that's the idea behind this kind of proof of art with ZK and where it's going and some of the stuff that I'm thinking about now. Definitely open to collaboration if this is something that you're interested in or if it gets your juices flowing. And I would just like to thank you all for your attention as I've walked you through some of these early research directions and where I'm going. And yeah, I think that's about it.
Oh, thank you so much. That was great. Awesome. We covered quite a lot here, from philosophy to technology to different intersections between the two. Also, we already have a question by Alan. Do you want to go first? And again, I guess it's just a general reminder that if you guys want to ask a question, feel free to raise your hand, or if you can't unmute, just put it in the chat and then I will ask it for you.
So it sounds like some of these problems could be solved, and I put in with a question mark more simply, with homomorphic computation, encrypted inputs, encrypted computation, and encrypted output. Is that correct?
Yeah, and absolutely. I think homomorphic encryption has a huge role to play. A lot of the ZK systems that you would employ are homomorphic, right? So the circuits that you're creating as a prover or that you're initializing as a prover are usually operating in a homomorphic space. The circuits are logical gates that operate on encrypted data. So it is in fact a homomorphic, it's a homomorphic operation that you're computing. I think the problem with homomorphic systems is there is a distinction between fully homomorphic and I guess what you would call partially homomorphic, where you need to rely, so you have full Turing completeness over, any arbitrary input or data, and you can perform any computation like multiplication, addition, exponentiation, etc. That becomes really difficult to do at scale. So say if for example, you wanted to run a predictive algorithm on the weather using a very high resolution multi-spectrum satellite imagery of the planet, the amount of energy and computation time that you would need would be infeasible. So what you can do though is break the problem up into small pieces and solve within specific compartments. And one topic that I definitely wanted to talk about, but couldn't squeeze into the preparation for this in time, is this idea of Kolmogorov complexity. So what I really love about, pushing just computer science and systems design for solving real problems in the world, like predicting the weather or what have you, is it forces us to be more judicious in how we allocate our compute power, our GPUs, our CPUs. And this brings us back to this idea of complexity by Kolmogorov, a famous Russian mathematician, which is that you can define something as complex as, you can define the complexity of something as how many steps it takes to produce that output, as a program to produce that output. A human being's program would probably be the developmental steps. Let's say just a human being at birth would be the developmental steps or the program to produce that complex, So what you can have as an objective function is to reduce some of these challenges with homomorphic encryption. You can have an LLM or some other, more capable, entity, say a very good LLM that could optimize for Kolmogorov complexity while creating new types of circuits that make it more feasible to homomorphically compute on these large data sets and be able to, more easily approach the full approximation of the digital Earth twin problem.
Yeah, and homomorphic encryption is being used in limited case at scale. Microsoft is actually using it for search. They're using a homomorphic computation so that both your search query and the result is unknown to them, which I thought was interesting. And that's being used today, I learned. I do have a simple example, a real life example of having your science conflict problem. If nobody else has a question, I can tell the story. Back in I guess it was the late 80s, there was a failed satellite launch. And the two companies, as I recall, it was Boeing and Lockheed. And one of them, I don't remember which one, had the rocket model, and the other one had the telemetry data. And they didn't want to share it with each other. Neither one didn't want to give up the program, and the other one didn't want to give up the data. And I got called in to consult on this at NASA for reasons I have no clue. And my solution was something I called the firing squad solution. In a firing squad, one of the soldiers has a blank, so everybody can justify not having killed somebody. That's the idea. So my idea was you produce 5 programs, only one of which produces the correct result. And it's very easy to produce reasonable looking but incorrect results. And the one with the data produces 5 data sets. One's at the actual data set and one that looks, and 4 that look actual. And NASA only knows which one. They don't see the data or the program. And so NASA just assigns them to do 5 different computations, only one of which gets the right program and the right data. And that would solve the problem. And I found out a year later that what they did instead was they had 2 companies sign an NDA and they just shared everything. This was a real life example of that problem.
Yeah, that reminds me of the black hole imagery research project. I forgot the name of the consortium, but where there was multiple teams all throughout the world that stitched Lego, right? I think it was Lego that stitched together each of the images that were taken of the first black hole observation. And these teams were all put into relative isolation to try to approximate what the best description was, what model best fit the data. And then after the fact, they would all compare results and they would converge on, the best model. So the idea there is you didn't want to have groupthink and push forward one interpretation because everyone's cross-contaminating each other. I think there definitely is. I think there definitely is a use case for cryptographic verifiability to prove that you are following some series of steps and that you can compare and reproduce those in different environments. But, I think also there is an important distinction to be made when open source and open data is important, and when it's important to be judicious about when we release that information or when we release that data. So I think I can practice the reality can be pretty complex.
Isn't there a problem though with code coverage and doing these proofs, that the whole thing is too complex to prove or verify the whole thing? And so part of it has to be reducing it to recording the output, the actual output, and then you have a code coverage issue.
Oh yeah, absolutely. One of the projects I really can follow closely is a ZK programming language called Keylong, named after one of the Taiwanese cities. And Keylong is written in Haskell, so it's strongly typed, and you can actually formally verify every single execution trace down to the compiler.
Yeah, and the SEL4 kernel has been proven in that way. But even though that's an operating system kernel, it's far simpler than a weather prediction. And so that's the question when you get to these 100 million lines of code simulations. I don't think it's practical to prove the whole thing.
Yeah, I would agree with you there.
Okay, let's see if there's any other questions, comments. Feel free to raise your hand. I have a few questions that I think are usually of interest to the Foresight community. So if you want to ask your specific questions, you can stop me by just raising your hand. But I think in principle, you've laid out almost like an epistemology here, and then give you also implications for specific technological applications on it. And I'd love to know if things pan out in this research direction as you think, then what progress do you think, could you be making in 5 years or so? Like, where do you think this may eventually really impact the world? Or, where could we learn the most about the way that we use technological systems or could improve our use of them?
Yeah, that's a really good question. And I think it's the right sort of question to be asking early on in a research project when curiosity, I think, threatens to overwhelm they'll predict the long-term outcome of why you're doing this in the first place. What would be really captivating for me is in 5 years, having a set of tools that allow me to scrape the internet for data that I knew came from certain sensors or certain data collection points, trusted data, and being able to produce results that can then be combined, that are composed. So I think if we had these sorts of primitives for computational reproducibility, and it doesn't have to be at the scale of a digital twin of the Earth, although it's, I think, thought-provoking, we would probably see a revolution in major computational sciences, as well as a shift towards existing fields of science that aren't yet computational, like psychology, or perhaps, yeah, I would say like biology as well, which is making that shift over. And I think what's key there is it'd be a lot easier, I think, for researchers to formulate distinct, unique research questions and to be able to build upon each other's work. Maybe 5 years is a little ambitious for that, but I think if we broaden the horizon a little bit and think farther down the line, I think what we'll really see if this type of technology comes to fruition is fully computable, basically a base layer of a fully computable knowledge corpus, where you have some cryptically verified data that's collected by sensors or drones that are running their own operating systems that you can prove are following some, say, like some search space algorithm, and you can be able to rapidly test different types of hypotheses faster than you would having individual research labs across the world within, their confines, starting from scratch each time and collecting the data from scratch. So this idea of a shared, like, low-level data fabric that can be used to assemble building blocks for knowledge in a computational, semi-automated way that is still supervised by experts, I think, is a really compelling idea. It gets at this concept of having a perpetual science machine or a perpetual knowledge gathering machine that's constantly collecting data and testing hypotheses and ranking them in terms of explanatory power. So I think that's the big picture boyish vision that I have for where this research direction could go.
Our level perpetual science machine. I wonder if it's, as much of an impossibility almost as the perpetual motion machine, but it's definitely, I love the ambition of it. Really cool. And, it's just, from a, I guess, more logistical level almost, is this a project that is relatively separate to your normal work? And like, how did you even, come up with this? How did you generate the idea? And does it influence your day-to-day at all? Or is it mostly relatively separate?
Yeah, I think this idea, I started incubating during my PhD work when I was working with really large data sets and had to deal with reproducing the data in the same computational environment. So to give a little bit more grounding, we have these brain images, and these brain images have like all sorts of errors, and they require manual editing if you're trying to reconstruct them into 3D services to create population averages that you can use for predicting disease or age or whatever. And so we would have these editors that were distributed all around the world or all around the country at the time, and they would have to execute some code on this, multi-terabyte data set, and they would have to do so on their machine reproducibly every single time and then combine the results from everyone else. So that got me thinking, like, how do I solve this problem? This is really hard. And there were some tools at the time that helped us go most of the way there, although it still required tons and tons of manual work. But I started thinking, as I was building software, how could I generalize the basic tools to make this more possible? And I think at its core, it's an epistemological problem. In terms of my day-to-day, I am involved primarily in Holonym Foundation, working zero knowledge proofs, and a lot of the pure research that I'm exposed to there directly informs the complexity with which I can describe or tackle this problem. So in terms of moving forward with this, I do think at some point in the future, I'm also a scientific advisor at the Active Inference Institute, and there's tons of shared overlap in terms of the goals or research directions that are present there. If you're familiar, active inference is a computational model for how we can describe behavior, especially in complex or noisy environments. So my medium to long-term goals are probably bootstrapping some small research group to go through journal clubs and build out maybe some proofs of concepts and maybe write a couple scientific articles along these lines.
Very cool. And then what's next with Holonym?
Yeah, Holonym. Yeah, we got some stuff going on. So Holonym v3 is coming out soon. So Holonym it's a zero knowledge protocol for key custody and proofs on identity. So what that means is it provides you basic tools for taking your cryptographic keys, signing data with it, using it to interact with other distributed systems such as a blockchain or pulling or pushing data to a distributed data network. And with V3, one of the really core components is being able to prove that you are the same person, even though your identity might not be completely known. Previously, with V2, we've relied on government ID, basically showing your government ID and then having some third party verify that it exists in some database, that it's a real ID, hasn't been copied, and handing you back a signed cryptographic credential that they then can't track. So they know that you verified, but they don't know who you are, besides that they can't attach a specific public key to that, to an identity. So that's undesirable because we don't really want to reveal any information if possible at any point to anyone. So with V3, we're using near-field communication chips, so things like e-passports and certain types of national ID documents that have these chips embedded in them. And you basically tap them to the NFC antenna on your phone, and you're able to verify that this credential was signed by the government, that it is a one of one, and that it hasn't been tampered with. And you can basically make proofs on identity on a local device without leaking any data in zero knowledge. So we've been working pretty hard on optimizing proof generation on consumer devices, which is going to be, I think, a real game changer. So imagine, for example, where this would lead is you would have in your Apple wallets individual private credentials that are mathematically verified to have certain attributes issued verifiably by the state or by some government entity. And so in the long run, this could be used for authorizing border travel, for authorizing gated access to privileged, so proving you're over 18 or have rights to be in a certain area, et cetera. But primarily what we're working on is including V3 along with a wrapper called Silk, which provides a secure and friendly interface for key custody with security. So if you, for example, one of the major things in self-sovereign distributed systems is you want to be able to custody your own keys. You don't want to have a server holding your keys for you because then that defeats the purpose. So once you have these NFC type credentials, actually, you can recover your keys from a distributed network after you've lost them. So it solves like this lost seed phrase problem that, the Bitcoin and other communities have been having trouble with.
Very cool. I would certainly need the proving over 18 feature. I just got banned from Lyft because several drivers have reported me for being underage, which is adorable. I'm like, was double involved now. Anyway, it would definitely help me.
That hasn't happened to me for 3 years.
No one knows why, Ellen. No one knows why. Okay, Shadi, are there any final things that, you wish I would have asked, or like any next steps, or how people can contact you and, request for collaboration?
Yeah, absolutely. If you're interested in the art project, do reach out. My name is just shady@holonym.id. Definitely looking for collaborators there if you want to push the boundaries of, what computational mathematical art can look like. The other plug I wanted to make is if this idea of a perpetual science machine, as ridiculous as that sounds, interests you or excites you, we are organizing the third annual DeSci Summit in Denver, which Allison and I have had the pleasure of working with in the past. That's where we first met. And yeah, we're looking for contributors there, either volunteers that would like to help curate talking points or ideas. The main two topics are technological and coordination layers for open science networks. And then the second is how do we build DAOs around scientific research? Yeah, so if you're interested, do hit us up. The website is here if you want to see what happened last year. And the event will be held in Denver from the 25th of February to the 1st of March. And we'll have stuff at ETH Denver. And then we'll also have a venue at the University of Colorado in collaboration with the Stem Cell Center there.
Wonderful. Thank you so much. Really appreciate you coming on. Hope you have a wonderful time at East Denver. Thanks everyone for your interesting questions and fun stories, Ellen. And I hope to see you all very soon for the next one. Have a good one and enjoy your day. Thanks a lot for Shadi for coming on, and see you soon.